we discussed the difference between the primary energy use and the secondary energy use. Secondary energy use is the energy used by the end customers, whereas the primary energy use includes the resources associated with producing the energy as well as transporting the energy to the end customers. Now, the conversion of secondary energy to primary energy is influenced by a number of factors. For example, how the power is produced in the country, what portion of electricity is generated from each source. If we compare India and USA, more than 3/4 of the electricity is generated from thermal power sources. However, the emissions per unit amount of electricity generated in India is more than the emissions per unit amount of electricity generated in USA, because we use more coal for producing electricity, whereas US uses substantial amount of natural gas for power production. Now, the power mix for each country varies from location to location. For example, in France 90% of the electricity is generated from nuclear power plants, whereas in Norway most of the power is generated from hydro power plants. So, the power mix for each country varies, and that influences the primary energy use associated with the energy consumption. Now, we have covered the simple indicators of sustainability. The next section is the composite indicators of sustainability. So, we have 3 indicators: ecological footprint, eco efficiency and eco label. Ecological footprint is a concept developed at the University of British Columbia. Basically, this relates the resource consumption per person and the capacity of ecosystem to generate resources and absorb wastes. This is a quantitative measure for assessing the resource use, ecology, economics and urban development. Ecological footprint is formally defined as the area of the land and water bodies required to produce the resources consumed and to assimilate the waste generated by that population on a continual basis wherever on earth that land or water bodies may located. This picture symbolically represents what ecological footprint is. The first line shows the area occupied by a community or a city, and the second line here, it shows the ecological footprint of that particular city. So, always the ecological footprint is much higher compared to the actual physical area occupied by the cities. So, this is one of the reasons why we call cities as incomplete ecosystems, because the land area occupied by metro cities is less than 1% of the aggregate ecological footprint of that city. A comparison of ecological footprint of different countries. So, as we see from here, the ecological footprint of an individual in US is 8 times higher than an ecological footprint of a person in India. In Europe, it is about 5 times higher than India. China, South Africa and Brazil, it is 2 to 3 times higher compared to India. So, in terms of ecological footprint per person, in terms of per capita carbon footprint, the lifestyle of an Indian citizen is much sustainable compared to any other country in the world. The second composite indicator for sustainability is eco efficiency. Eco efficiency is a concept developed by the World Business Council for Sustainable Development, WBSCD. So, basically here we are trying to relate the mass of the product manufactured and the net sales of the product to the amount of energy used, the amount of raw materials used and the amount of emissions generated during the product manufacturing. So, the basic idea is to evaluate the cost implications and the environmental implications of different design practices and manufacturing practices, and choose what is best in terms of cost and environment. So, this figure graphically shows the concept of ecological footprint. So, we are relating the mass of the product sold to the amount of energy used, the amount of raw materials used, and the amount of greenhouse gas emissions generated from the process. The second chart relates the net sales of the product to the amount of energy used, the amount of raw materials used, and the amount of emissions generated. So, basically the eco-efficiency relates the economic indicators and the environmental indicators. Now, what are the benefits of using eco-efficiency ratios for a product? So, measuring eco-efficiency for a product helps us to use less amount of resources in terms of materials, energy, water and land use. It helps us to reduce the environmental impacts in terms of emissions, waste generated and toxic chemicals released into the environment. It helps us to increase the value of the product in terms of functionality, flexibility, service life, durability and recyclability. The other composite indicator for sustainability is eco-label. Eco-label is developed based on the use of raw materials, energy, land use and pollution generated to land, water and air. See, the first eco-label program in the world was released in Germany. It is called German Eco-Label. This was created in 1977 to promote environmentally friendly products. So, the participation in this scheme is voluntary. So, basic idea is to create awareness in preserving the use of natural resources. Okay, so, these are different examples for eco-labels. There are different ratings to state how green the product is. For example, the Energy Star rating by US, the FSC rating for timber products, eco-label rating by European Union, and then certification schemes for seafood and so on. So, that completes the first part, where we have covered the definitions of sustainability, the life cycle of the product and the different phases in the product life cycle, different definitions for sustainability and the indicators for sustainability, the simple indicators and the composite indicators for measuring sustainability. The second part, we cover life cycle thinking, industrial ecology, principles of green engineering, biomimicry and some information about the relation between technology and human factors. Life cycle thinking. Life cycle assessment is a scientific technique used for evaluating the performance of a product in a holistic manner, considering the entire life of the product, starting from mining of raw materials to the disposal of the product. So, we consider all phases of a product life cycle: mining, manufacturing, transport, distribution, use, maintenance, repair, rehabilitation, disposal, recycling and then landfilling, incineration and so on. Now, the findings of life cycle assessment can be presented using a spider chart like this. This is called as an eco profile, where we compare the performance of different alternatives on multiple indicators. For example, energy, water, resources, waste, CO2, acidification, eutrophication, ecotoxicity, human toxicity and so on. So, this is a very powerful plot to evaluate the sustainability performance of multiple alternatives for a product. So, in this case there are three alternatives considered. One is a base case, which is conventional. Second is the feasible case. The third is sustainable case. So, in case of life cycle thinking, we evaluate the product considering the entire life cycle. We do not come up with a biased opinion based on selected phases of a product. For example, if I compare electric powered two-wheeler with a petrol powered two-wheeler, just based on the operational phase of the product, the conclusion will be the petrol powered two wheeler results in emissions, whereas electric powered two wheeler produces 0 emissions. But that is not the true picture. We have to consider the entire life cycle in evaluating the performance of the product. For example, I will illustrate the concept of life cycle thinking using this example. Let us consider two buildings. In the first building, the core and shell of the building is made of structural steel. In the second building, the core and shell is made of reinforced cement concrete. Now, let us compare the life cycle performance of these two options and which is sustainable, which is producing more amount of impacts to the environment. Now, let us compare by individual phases of the building life cycle. If I only compare the amount of materials used in these two buildings, the energy associated with materials in the first option, that is the structural steel framed building, is much higher compared to concrete building, because the embodied energy of steel is higher than the embodied energy of concrete. So, as a result, the total embodied energy, the initial embodied energy associated with the structural steel framed building is higher compared to concrete framed building. Now, if we compare the site practices, the assembly of the building at the site, assembling a concrete building takes more energy compared to assembling a steel building in a construction site, okay, because in case of steel building, all we need is welding and bolted connections. So, it takes relatively less energy compared to a concrete framed building, where we use several heavy machineries like a batching plant, tower crane, concrete pump, concrete truck and so on. So, based on materials, steel building is more energy intensive. Based on construction practices, concrete framed building is more energy intensive. Now, if we compare the operational phase of the two buildings, the energy use is expected to be comparable, because the core and shell does not influence the operational energy much. Okay, so, from the operational point of view, both buildings are expected to be comparable. Now, considering the end of life phase of the building, the demolition energy associated with steel framed building is expected to be less compared to the demolition energy associated with concrete framed building. So, in the individual phases, considering materials, we conclude that a steel framed building is more energy intensive. Considering the construction and demolition practices, we conclude that the concrete framed building is more energy intensive. Now, if I compare the entire life cycle of both buildings, starting from materials to end of life, now the conclusion is that the performance of both buildings are comparable. Okay, one is not better than the other, both are comparable, and there is no significant difference in the performance of the two buildings. That is what shown in this plot. So, this figure shows the comparison of a steel framed building and concrete framed building with respect to materials, construction, end of life, and then all phases together. So, this demonstrates the significance of using life cycle thinking in evaluating the performance of any product. If we evaluate based on one or two phases, then there is high probability that we end up having a biased opinion about the performance of the product. For example, I want to apply the concept of life cycle thinking for a two wheeler. Let us say I compare a petrol powered two wheeler with a battery powered two wheeler. Now, the questions that come to my mind related to life cycle thinking are: what is the embodied energy associated with the battery used in the electric powered two wheeler or battery powered two wheeler? Second is, do we use hazardous substances in manufacturing batteries? Third, with respect to maintenance and repair work, how often the battery is replaced? What is the energy use associated with repair work and replacement? So, in other words, what is the recurring embodied energy associated with replacement of batteries during the life of the electric vehicle? The fourth, what is the cost associated with handling the hazardous substances present in the batteries in the end of life phases of the component. So, to holistically evaluate the performance of a battery powered two wheeler with a petrol powered two wheeler, we have to answer these questions. Okay, then we will be able to say whether a petrol powered two wheeler is better or a battery powered two wheeler is better. Otherwise, comparing just based on the operational phase may lead to a biased opinion about the performance of the product. Now, we will also go through some principles of green engineering. So, this is related to the field of industrial ecology. So, industrial ecology is basically the application of ecological principles to industrial systems or ecological restructuring of the industry. So, the basic idea of industrial ecology is rejecting the concept of waste, okay, how to eliminate waste in terms of materials, energy in the manufacturing processes, thereby improve the efficiency of the processes, and how to close the life cycle of a product by connecting the end of life back to the product manufacturing. So, that we are moving towards zero waste, zero emissions to water and air. So, this is also related to the Make in India movement, where we focus on zero defects and zero effects. Zero defects aim to have no rework, zero effect focuses on zero discharge to air, land and water. Now, what are the ecological principles that we are trying to integrate into the manufacturing processes? Use of renewable resources, avoid the use of hazardous substances, moving from a linear economy to a circular economy, and then promoting diversity and adaptation in a manufacturing system, and then consider the entire life cycle cost, not just the initial cost of the product. There are different ideas related to the field of industrial ecology. I have listed few here. The first is industrial symbiosis, which promotes the use of waste generated from one system as a useful resource input for another system. The second is design for environment, which focuses on changing the design processes to promote better reuse and recycling of the product in the end of life. The third is industrial metabolism, to understand the resource use and waste production to achieve resource efficiency. The fourth is cleaner production, which focuses on systematic reduction in material use and the control and prevention of pollution throughout the life cycle. So, the 12 principles of green engineering that we are going to cover are generic in nature. It can be applied in any sector at any level. For example, it can be applied at a molecular level, it can be applied at the product level, or it can be applied at the urban architecture level. Molecular level, for example, designing a chemical, developing a chemical. Product level, developing a material, or urban level, developing cities, developing urban settlements and so on. So, the first principle is designers should ensure that all materials and energy inputs and outputs are as inherently non-hazardous as possible. So, the basic idea is eliminate the use of hazardous substances in the supply chain, in the manufacturing, in the assembly processes. Thereby, we make the end of life treatment much simpler. Okay, even when there is a lapse in the end of life treatment, there is no impact to the environment. The second is, it is better to prevent waste than to treat or clean up the waste after it is formed. Okay, prevention is always better than cure. So, eliminate the generation of waste rather than treating them after it is generated. Third, design for deconstruction and disassembly. Consider the way the product will be disassembled and try to change the design practices in such a way that you maximize the recovery of useful components in the end of life. Fourth is eliminate waste and inefficiencies in terms of time and cost in manufacturing processes. See, for example, this is a Rinker School of Construction building in University of Florida, Gainesville. So, this is a US LEED Gold certified building. This building has been specifically designed for deconstruction. So, that means when the building is designed by the architect, they also have developed a demolition manual which will be available to the contractor after the service life is over. So, that demolition manual clearly states how the building should be disassembled at the end of service life, thereby maximizing the recovery of useful components which can be used in other construction projects. So, this substantially reduces the amount of waste that is sent to landfills. So, the other principles of green engineering, it may be counterproductive to spend too much energy and cost to recycle a complex product. Is it productive to recover the useful materials from a computer chip in the end of life? Okay, so if that involves the use of hazardous substances, then it is better not to recycle. The other principle, whether to recycle a product or not, should be based upon material and energy investment. Avoid the use of hazardous substances or high amount of energy for recycling. Okay, if the recycling process involves high amount of energy or hazardous substances, then that can be avoided. Products and processes and systems should be output pulled rather than input pushed throughout the use of energy and materials. Just in manufacturing to meet the consumer demands in terms of time and quantity and quality, avoid overproduction and waiting and excessive inventory built up in the factory. Targeted durability, not immortality, should be the design goal. In other words, design the product exactly for the required service life, do not over design the product for eternal life. Okay. So, design for unnecessary capacity or capability, that is one size fits all, should be considered as a design flaw. Okay. So, the basic idea is do not over design the product, design the product exactly for the required service life. And finally, use output from one system as input for another system, which is nothing but industrial symbiosis. For example, we use fly ash generated from thermal power plants as a useful resource materials in cement factories where cement is manufactured. Materials and energy inputs should be renewable rather than depleting. Whether a substance or energy source is renewable or depleting can have far reaching effects, for example, bioplastics, and these 12 principles of green engineering will facilitate the movement towards sustainability. Systematic integration of these principles is key towards achieving genuine sustainability for the benefit of environment, economy and society, and the ultimate goal of sustainability. Biomimicry is basically the use of lessons from ecosystems to develop a concept of sustainability for humankind. So, developing a new class of materials that are strong and lightweight and can be decomposed into the environment in a harmless way. So, basically in biomimicry we are trying to answer these questions. Does it use renewable resources? Does it use only the energy it needs? Does it recycle everything? Does it reward cooperation? Does it encourage diversity? Does it use local expertise? Does it curb the excess from within? Okay, so these are some of the questions we are concerned in biomimicry. Other concepts related to sustainability: extended producer responsibility and extended supply chain. Extended producer responsibility. So, basically the manufacturer of the product takes the responsibility to handle the end of life after the service life is over. For example, this concept is predominant in Germany, where the manufacturer of a car takes the product back after the life is over. The amount of waste that is sent to landfills is reduced, and the recovery of useful components from the product is maximized. Technology and human factors. So, if we consider the relation between technological improvement and human factors have more influence on the consumption of resources compared to technological advancement. For example, let us consider cars manufactured with better fuel mileage, or the production processes that use less amount of energy and resources. That is good. We are having better products, we are having better efficiency in terms of manufacturing the product, thereby we are using less amount of raw materials, but technology alone is not sufficient to make progress towards sustainability, because if you count the number of products sold in the market per year, the total impacts are much bigger compared to the technological efficiency achieved in the manufacturing. For example, what are the negative impacts of more product lines by the customers? Consumer oriented lifestyle. Okay, so overconsumption nullifies the benefits reaped because of technological advancement in a country. Technology cannot substitute irreversible changes made to the ecosystem. Okay, technology is not the solution for everything. Okay, so unless the human changes his behavior, unless the consumer changes his behavior and makes the lifestyle more oriented towards ecosystem, technology only complements that. Excessive use of resources and waste becomes a cause of embarrassment rather than a symbol of prestige. So finally, what is the way forward? We have to lead a eco-friendly lifestyle, reduce, reuse, recycle and remanufacture in any system. We have to de-energize, reduce the energy footprint of products, materials, decarbonize, reduce the carbon footprint of materials, detoxify, reduce the use of hazardous substances associated with manufacturing. We have to create more awareness among the consumers to have a lifestyle that matches the ecosystem, have an eco-friendly consumer behavior and lifestyle. That is the final way to promote sustainability in the country. Okay, thank you for your kind attention. Thank you.